Hey everyone, and welcome to the lab. On behalf of Forge College, I am super excited to dive into this explainer. The title of today's session is Framing the Pattern Catalog and Translation Approach. We're taking our from EVM to SVM, transitioning from Ethereum to Solana track to the absolute next level. Now, if you recall, in our previous lesson, we were drafting pattern entries for events and errors. Well, today, as part of our From Solidity-to-Rust and Anchor module, we're building out the actual capstone. We are creating a master blueprint for translating Solidity code into Rust and Anchor. So if you've ever tried to port an Ethereum smart contract over to Solana and found yourself just, hopelessly lost in a maze of account constraints, banging your head against your keyboard, you are in exactly the right place. We aren't just hacking code together today. We're building a rigorous, repeatable system. So, moving beyond our previous tinkering, here is our blueprint index for today. We're going to cover the grand catalog scope, then the anatomy of an entry, side-by-side code mappings, our translation workflow, and finally, fidelity versus idiomaticity.
All right, let's jump straight into Section 1, the grand catalog scope. We really need to define our boundaries here.
To keep things clean and avoid building, a chaotic developer junk drawer, we have to be super clear about what goes into our catalog. So what is a catalog entry? A proper entry isn't just some random code snippet you blindly copy-pasted from a forum at 3 in the morning. No, it's a meticulously documented bridge between the Ethereum virtual machine and the Solana virtual machine. It must be explicit, it must be testable, and it absolutely has to be completely reproducible for anyone else looking at your work.
So what makes the cut? We are specifically targeting canonical, recurring EVM patterns. We're talking about core concepts like ownership and access control, reentrancy guards, and pull versus push payment flows. And what are we rejecting? We are ruthlessly tossing out external infrastructure patterns. Things like Layer 2 rollups or off-chain oracles just don't belong here, unless they heavily, and I mean heavily, interact with native Anchor account modeling. We have to keep our focus laser sharp.
Moving right along to Section 2, Anatomy of an Entry, where we establish the required metadata.
This strict set of machine-readable fields is basically the beating heart of our blueprint. Every entry needs an ID, a title, category tags, explicit code examples for both Solidity and Anchor, links to tests, and diagnostic notes. By enforcing a JSON or YAML schema, automated CI checks will instantly flag any lazy developer, maybe even future you, who tries to submit undocumented code. This metadata ensures our catalog is searchable, indexable, and universally understood.
Okay, Section 3. Side-by-side code mappings. Time to expose those mechanical differences.
Notice the fundamental shift in architecture here. Think about a simple implicit Solidity constructor. Super easy, right? But when you map that over to an Anchor initialized instruction, things change drastically. It now requires a specific payer and an explicit account serialization space. You actually have to do the math. 8 bytes for the discriminator, 32 bytes for the public key, and so on. This isn't just a syntax change, it's a critical operational shift regarding how memory and rent work on Solana, and you absolutely must document it in your catalog.
And here is where the real magic happens. How do we handle access control? While Solidity enforces ownership with a slightly clunky runtime required check executed during the function call, Anchor allows us to elegantly express it with declarative constraints. By simply adding a macro like has1=owner to our struct, we are telling Anchor to perform this check before the instruction even runs. It's cleaner, it's safer, and honestly, it's a completely different mental model.
Furthermore, validation errors map completely differently too. In Solidity, you might be used to throwing custom string revert messages like not owner, but over in Anchor, we utilize custom error codes as part of a diagnostic enum. So the crucial takeaway is that your catalog must explicitly pair those Solidity revert messages with their equivalent Anchor custom error codes to maintain absolute testing parity. If your contract fails, it needs to fail in exactly the same conceptual way across both chains.
Next up is Section 4, the translation workflow. Let's build a repeatable engine. Here is our 5-step assembly line. Step 1, always start by stripping the Solidity code down to its absolute bare minimum semantics. Remove all the fluff. Step 2, draft the native Anchor equivalent. Step 3, document the mappings and any weird quirks you found. Step 4, write tests to prove both versions behave identically. And finally, Step 5, evaluate and score the result. Sticking to this engine guarantees consistency across your entire capstone project.
Finally, Section 5, Fidelity versus Idiomaticity. This is all about evaluating quality.
The first axis we measure on is fidelity, graded on a scale of 0 to 5.
Fidelity essentially asks, how closely does your anchor translation preserve the original contract's semantics, state transitions, and failure modes? A perfect fidelity score of 5 means your translation is a behaviorally flawless mechanical replica of the original EVM contract. The observables are identical, the failure states match perfectly, it's functionally a clone.
But honestly, cloning isn't always the goal. That brings us to our second axis, idiomaticity, also graded 0 to 5. Idiomaticity measures whether you've built a native Solana masterpiece. Are you correctly using program-derived addresses? Are you leveraging declarative account constraints? Or did you just blindly force EVM logic into Rust syntax, effectively treating Solana like it's just a faster Ethereum?
To put that into perspective, let's say you perfectly duplicate a Solidity control flow by writing a bunch of manual, low-level if statements inside your instruction logic, completely ignoring Anchor's built-in macro constraints. Well, you might score a perfect 5 for fidelity because it behaves identically, but you would get an embarrassing 2 for idiomaticity. You've basically written Solidity in Rust, and any experienced Solana developer looking at your code will immediately know you're a tourist. Our goal is to balance these two scores.
As you build out your capstone projects, I want you to remember this core engineering principle. Prefer clarity over cleverness. If you ever have to break parity to make the code more idiomatic to Solana, be totally clear about it. Document all your intentional divergences right there in the diagnostic section of your metadata, and leave the clever, undocumented hacks at the door. I promise, your future teammates will thank you.
To wrap up this explainer, I want to leave you with a provocative thought. If we're making our metadata schemas strictly machine-readable and meticulously pairing EVM patterns with their SVM counterparts, how close are we to fully automated, AI-driven cross-chain translation? By structuring our knowledge this rigidly, we aren't just helping human developers today. We are literally laying the foundation for the automated future of Web3. To continue mastering these vital systems and to actually get your hands dirty writing some Anchor code, make sure to visit forge.college. On behalf of Forge College, thank you so much for joining me in the lab today. Keep building, keep cataloging, and I'll catch you in the next explainer.